Welcome, everybody, to the proof practice page. So, the big kahuna, this is what all of geometry is really based around. We will use this in every chapter for sure. I was going to say every lesson. It's that important. Proofs are what geometry is really all about. So, let's jump right into it. You're going to hear or see this word justification used a lot throughout the page, and I just want to make sure you knew what that is. It's just the reasoning that you use to draw a conclusion. So how do you know that you can do that kind of thing? Two other terms that are very particular to math and especially geometry in particular are postulate and theorem. So postulates are also called axioms. They're a little different, but you don't need to know the difference at this level. It's just information that can be known without needing a formal proof. So one of my favorite examples to illustrate the difference between a postulate and a theorem is when you talk about triangles, right? On a triangle, a couple things we know, or that I know, is that they're going to have three sides and that their interior angles add to 180 degrees. Always. The interior angles of any triangle always add up to 180 degrees. The first bit here is a postulate or an axiom. You don't need to sit down and prove that your triangle has three sides. If it didn't have three sides, it wouldn't be a triangle, right? So that's the idea of information known to be true without needing any kind of proof. Now, a theorem, on the other hand, is when you probably should, or somebody has already sat down and proved it to be true because it's not just obvious. Like when I look at that, I wouldn't immediately know. Like if I asked a kindergartner how many degrees is in that triangle, they wouldn't tell me 180 degrees. It's not obvious, right? Somebody had to, and also if I changed the triangle, who would have guessed that these two triangles add up to the same amount of angles on the inside? If I add this, and this angle together, it's the same as this, and this angle, right? It's not obvious by any stretch of the imagination, but somebody has sat down and proved it before, so therefore it is a theorem, and we can use that information to create or deduce new information. All right, so that's two words you're going to see a lot of for the rest of the year, postulates and theorems. There's a subtle difference, but mostly it's just things that we know to be true. All right, getting into some of the properties of real numbers that you saw in your first video. What I'd like you to do is to try to work with this a little bit more just to really solidify it, because I'm pretty much just assuming you understand this moving forward. So what I want you to do is go through and match each of these properties with the examples that have been provided here. So like, for example, x equals 3 and 3 equals x is an example of the symmetric property, because something forward and backwards seeing its mirror image is what symmetry is all about, right? So that is the symmetric property. Go through and try to fill in which property goes with each example, and then we can go over them together. All right, hopefully that wasn't too terribly difficult. Some of them are pretty obvious, like when you got a number outside of parentheses, hopefully your brain automatically at this point starts thinking about distributing, right? So yeah, that's the distributive property. Here we have x equals 9, and then I add a 3 onto both sides of that equal sign. That is an example of the additive property. The most useless one, the reflexive property, just means that something equals itself. This is used in like super formal proofs that like people that are really serious about making sure that this is exactly what I said it is. We'll use this. Maybe it comes up, maybe you use it sometimes. I'm never going to ask you to. You might need to identify it at some point, like it is here, but it's not that useful at our level. So moving on, division property, x equals 4. I divided both sides by 2. So that would be an example of the division property. Subtractive is I've got m equals 12. And again, there I have a minus now added to both sides, or a 4 being subtracted on both sides. Y equals 3. Both sides are being multiplied. Those are all ones that you've pretty well used since like 5th, 6th grade when you first started solving equations, and you may or may not have known that they had names. Didn't really matter. You had to learn how to use them, and now we're going to use them more formally, and we're going to want to be able to justify or use these words to justify the things that we're doing. So we'll get into that here in a minute. The transitive is similar to that law of syllogism we looked at in the last lesson, where if A equals B and B equals 4, then I can jump right from the beginning to the end and just say, all right, this equaled that and that thing equaled something else, well, the first must equal the last then. So A equals 4. That's called the transitive property. And then the most useful one is called substitution. When you have a statement and you know part of that statement equals a thing, you can take that thing and plug it into the other statement. So I could replace this y with a 2 and just do 2 plus 3 is 5. So that's how I'm able to say that x equals y plus 3. Well, x equals 5 in this case because that y, that's a 2, right? So you're substituting some information in for some other information in a different statement. Okay. Using a property. So when you first see an equation, I put this on here just to make a quick point. When you see that, hopefully your brain immediately thinks, oh, I need to divide in order to solve that. And so we're using the division property. I put this on here just to make sure I illustrate that it is not the multiplication property that's being used. Even though the original statement was 2 times x, it's not what is in the problem, it's what you're doing that you need to justify. So it's the division property that we're using in order to say that if 2x is in fact equal to 18, is what that's saying, then I can say that this is still the same problem. This is the same statement that is. Telling me that 2 times something is 18 is the same as telling me that that thing is 9. Those are equivalent statements because the division property of equality ensures that nothing has really changed between the first line and my second line here. These things are equivalent. Let me continue to illustrate what I'm talking about here, is that as we go through and solve this problem, what you've done up until this point is learn how to solve this equation. All right, I need to figure out what x equals. So you've been working on doing that. Now, to build into the idea of proofs, it's already been solved for you. You just need to justify how you know that you can do that thing. So like when you solve, hopefully your first intuition is maybe to distribute. 2 times 1 is 2. 2 times 3x is 6x. That's definitely what was done to get from this line to that. So how do I know, if this was the original problem, how do I know that I didn't just create some new problem? How do I know that's still the same as the original problem? Well, I know that because there is a distributive property, distributive property of equality that tells me when you distribute, you maintain the same value in your problem. You maintained equality. This is the same thing as this down here. Nothing has changed except the way that it looks. Right? So we used the distribute. Wow. Let's act like that didn't happen. We use the distributive property, because I can spell, in order to show that this is the same as that. We just rearrange some stuff because we know what we're trying to do. We're trying to get x equals a number, and getting rid of parentheses is helpful in achieving that. We're able to do that by the distributive property while maintaining the same equation, not actually changing the problem. So then I move one step further, and I have to kind of think here. How do I get from that line to this? 6x is still there. The 2's gone. Oh, and this side went down by 2. We subtracted. Okay. So sometimes you'll have to find what happened and then justify it. We used the subtraction property here. So this is the idea of justification, is you're just explaining how you know that you can do the thing that you did. And then obviously you finish it out by dividing, so we use the division property. All right, and I'm all about abbreviating, right? You don't need to write out the distributive property of equality every time, right? You can even probably drop prop and just say, if you write distributive, I know what you mean. You mean the distributive property of equality. Now, don't get too carried away with that. Make sure that I do know what you mean. But like in this case, I would know what you meant. So again, if you're not sure, ask questions when those scenarios come up. Ladies and gentlemen, are you ready to do actual geometry for the first time in your life? This is going to be a fill in the blank to construct your very first proof that you've probably ever done. So the way this works is called a 2-column proof, and it has one column where we're doing some stuff to try to prove some conclusion. We're given some information to start with. In this case, we have 2 givens. That point B is the midpoint of AC. So point B is halfway between AC. And also, the C is the midpoint of BD. So that means that these segments are equal. BC and CD are also equal. That's what it means to be a midpoint, is you split the two parts in half, therefore they are equal to each other. So what we can do is whenever you take information that was given to you, you're going to just write given. Like you can see it down here, means we're probably on this side going to use our other bit of given information. Every proof starts with a given. Maybe I should take that. Almost every proof any proof I can think of starts with a given. So we take something that was given to us in the original problem, and we have to take that information to end up proving something at the very end. Like when I look at this, I know right away just by the definition that AB is equal to BC. And I know that BC is equal to CD. But what I don't know just by looking at it is that AB is congruent or equal to CD, right? I don't know that these two are equal. That's not given to me right away. We can prove it pretty easily, and we're about to do that. But that's the whole idea here, is that we're given a little bit of information. We have to derive or figure out something new about the problem that wasn't directly given to us, and we have to justify how we came to that conclusion. So once we know that B is the midpoint of AC, you have to think, what can I do with that? Well, I want my conclusion to have line segments, so maybe I should start talking about line segments. And in fact, here, since it's already kind of filled in for us, think about what the definition of a midpoint is, especially the definition of what was given. B being the midpoint of AC, what's that definition? It means that line segment AB is congruent to BC. Right, I kind of already said that. That is the definition of a midpoint. That's what it means for those two things to be equal. That's what it means for B to be the midpoint of AC, is that those two things are equal. So we're going to repeat that then. We're going to grab our other given and say that C is midpoint of BD. And I know that because it was given to me in the original problem. And I can derive the same information from that using the midpoint definition again. Definition. I can say that if C is the midpoint of BD, which was told to me that it is, then that tells me that BC, this segment, is equal to CD, that segment. And there's always a little bit of cleverness that's required, right? So at this point, we're like, all right, well, that was what I was told, and that's what I can do with that. That's what midpoints are. Well, here's where you have to pull in a twist, something that gets us to our conclusion. Okay, if I know those things are equal, and I know those things are equal, how do I prove these are equal? Transitive property. Back over here, we're looking at if one thing equals another, and that thing equals something else, we can say that the first and last are equal. If AB equals BC and BC equals CD, I can go I can assert that AB is congruent to CD by the transitive property, because one thing equals another and that other equals something else. So therefore, these two are equal. I can say these two are equal. Oh, by the way, sorry. The 3 dots means therefore. It's a good practice to put that at the end of your proof so that the reader knows you didn't just give up, but like you did reach your desired conclusion. When we did, we got AB is congruent to CD. Ba-bang. That's it. You just wrote a proof. Well, I wrote a proof. You watched. Let's see if we can do it one more time with angles and no help, just figuring it out. So as we look at this, we've got some given information, actually 2 pieces of given information again. We're going to write a 2-column proof to show that the measure, whenever you see that M, it means the measure of angle 2 plus the measure of angle 1 has to be 90 degrees. And at first when I looked at that, I thought, well, that's obvious. It's right here. But that's showing the measure of angle 2 and the measure of angle 3 is 90 degrees. We want 1 and 2. This angle plus this angle apparently equals 90 degrees, and we need to figure out how we know that that is true. I'm hoping you can already see it. So, guys, I'm going to be honest with you right now. I hated geometry in high school because when I looked at that, I'm just like, oh, well, 2 plus 3 is 90 and 1 is the same as 3. So 1 plus 2 is, yeah, obviously, right? And I didn't want to take the time to prove this. I promise you these things get way more complicated. It's not always going to be common sense. I'm tossing you some soft pitches right now so that you can build up the idea of how these things work, right? They get more complicated. It's not always going to be common sense. And you're like, this is dumb. This is building a strategy that will let you analyze very complicated concepts and trying to prove things that are not obvious at all. So let's bear with me and try this together. So given that angle WXY is a right angle, we see that right there, and angle 1 is congruent to angle 3, write a 2-column proof to get this. So we need to end up here. Always keep that in mind where you're trying to end up at. I'm going to start with the first piece of given information. So angle WXY is right angle. And I know that because it was given. You can draw lines between them if you want. You don't have to. Helps me stay organized, so I kind of like to sometimes. So, well, the first thing that I notice about what I'm trying to get to is that it equals 90. So I'm going to go ahead and use the definition of a right angle here to say that angle WXY equals, or I should be particular, the measure of angle WXY. If it is a right angle, then I know that it equals 90 degrees. So I know that by the definition of a right angle. All right. So I started with a piece of given information, the exact way it was written, and then I used that to derive something new, even though it's kind of obvious because it's an easy problem. I did that right here. So I've moved a step forward. I've got it where it is equal to 90. Step in the right direction. Now, the next thing I notice is that WXY isn't the way that our final statement needs to be written. It's a sum of angles. So I might want to go ahead and write that now, where I'm going to go ahead and split up angle WXY into angles 2 and 3, because I noticed that in my conclusion, I want it to be a sum of angles. You've really watch what you're trying to prove and use that. That's my best hint for you, is use your desired conclusion to guide your thinking throughout this problem. So I'm going to say that the measure, or that, the measure of angle WXY is equal to the measure of angle 3 plus the measure of angle 2. And I know that by the angle addition property. You should have seen that in your first video, that angle addition is an axiom that you can just state, that we just take for being true. Or a postulate, that we know that when you add two angles that make a bigger angle, they're equivalent. This measure plus that measure equals the bigger measure. So we know that by angle addition. Now here is where I'm going to pull in my other given, because I don't want it written this way. I want it written as measure. I didn't finish saying, I started writing. I want an angle 2 plus angle 1, not angle 2 and 3. So here's where I'm going to say that angle 1 is congruent with angle 3. And I know that because it was given to me. To extend this table just one extra line, because I need 2 more steps to finish this out. One thing I need to do is to sub out angle 3 for angle 1, and then I need to sub out the measure of angle WXY equal to 90. And I'm going to do that in 2 separate steps because it requires 2 separate justifications. So I know that the measure of angle WXY is equal to the measure of angle 1 plus the measure of angle 2, because I know that 3 equals 1, so I can substitute the measure of angle 3 for the measure of angle 1. So that would be the substitution. And then finally, I can say that the measure of angle 1 plus the measure of angle 2 equals 90, because we knew that the measure of angle WXY equals 90. So again, here I could use the transitive property. 90 equals that, and that same thing equals the sum. Or I could use just substitution and say I'm replacing the measure of angle WXY with the 90. I like substitution. It's my good old buddy. And bang, that is all there is to it. all there is to it. I know it's very complicated. It is very cumbersome, but that's what it is, and it will get easier. It sounds kind of like contradictory, but as the problems get a little harder, the proof will get easier because right here it's almost like so easy. How do I go through and define all of these things? Like, is it really necessary to go line by line like this? It kind of is, because we're trying to build up fluency with this. We're trying to figure out how this whole system of proving things works. So I'm going through every single detail here. It's a good habit to go through every single detail, but you kind of get lost along the way because it's almost like too much, like common sense gets in the way. So at this point, I'm actually going to cut you loose. I want you to try number 6 on your own. You know that BC is congruent or equal to DE down here. I want you to prove that BD, this whole part, is equal to CE, this whole part there. Hopefully your brain's like, obviously it is, but that's the whole idea. You have to push past that and figure out how do you justify each step to prove that it is. All right, so go ahead and pause now and see if you can work out that proof. Let's see how it went. I guess so. Here we're only given one piece of information, that BC is equal to DE. There's really not too much. Like, use that common sense, right? We know that we need to end up at BD equals CE, and your brain's just like, well, obviously, if this is the same and these are the same, then these two are going to be the same. Like, you know that, right? Well, what you're doing there is you're taking a constant, something that's the same for both BD and CE, you're adding on the CD to both of them. That's the whole deal, guys. You just take it and look, you say, all right, I need to prove that. So I need to introduce this idea of BD and CE into the problem somewhere because it was not given. Neither of those segments are given in the original expression. I should actually have bars over all these. I'm sorry. Because these are line segments, and we are using segment addition to do this problem. Woo! There we go. All right. So it is BC equal to DE was given. Now BD, part of what we're trying to get, I'm introducing this new idea by saying something that was given plus CD. So I can take this BC and add on CD and get the BD I'm trying to prove is equal to something else. And I create CE in the problem doing the same thing. I take the DE that was given to me and I add on CD. So now DE plus CD is how I get the whole idea of CE right here. That's where it comes from. Now that I have the two desired pieces, I can take the original statement that BC equals DE and simply substitute. I'm going to take those parts, and I need to get it so that I can substitute these in. I need to make it so that BC plus CD, this part right here, I've got to get this down here, right? I need to set these two things equal. So what I did is I took the original statement, BC equals DE, and I added CD onto both of them. Just like when we were looking at the other side, and on the additive part where I had x equals 9, and I said I can add a 3 onto both of those, I took this BC plus DE and I rewrote that down here and I added CD because I know CD is the same on both sides. I can add it to both sides. Now I'm able to say, all right, well, now I've got BC plus CD, which is equivalent to BD. So I can plug that in right here. And I've got DE plus CD, DE plus CD. So I can plug in CE right here. And bada bing, bada boom. That's the twist right there, was being able to take the original, add on the extra bit. That's what your common sense was telling you to do, and end up with the thing that you wanted. Take a deep breath. It's supposed to be confusing. It's a very, very new way of thinking, very different than the way your brain typically works through things where you just look for shortcuts all the way. Here, you're having to stop and show every bit of thinking because common sense can lead you astray. You can look at things and say like, that's a 90-degree angle, and it's not. You don't know that it is. This is proving. You have to show every step of logic, every step of the way. All right, we've got 2 more to look at here. I'm going to go ahead and ask you to try to pause and attempt these again. Please, 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 I promise you, it is worth your time to try and fail if you don't know what you're doing. It is okay. This is a zero stakes game right now. There's no penalty to failing. But if you try and mess up and then see how I correct or do something different, it will stick in your brain better than if you just sit back and watch me do it. So please pause and try to go through this problem. You've got DI bisects. So DI is bisecting NDH. So that's telling me right away that it's cutting that angle in half. All right, that's the idea of bisecting. And what you're trying to do is to show that angle 3 is the same as angle 1, only knowing that DI cuts NDH in half. All right? And then once you get down here, if you want to go on further, you know that you've got a right angle at AEC, and you know you've got a right angle at BED. So these are both right angles. And you want to show that AEB, just this guy right here, equals DEC, this one right there. So again, it's going to use a lot of common sense if you really stop and think about it, but you've got to go line by line and explain. Also, notice this one's a paragraph proof. So a paragraph proof is where you just write out sentences instead of using a table. If you prefer the table, I super don't care. I hate paragraph proofs as well. They are very annoying and very time consuming. I'll write mine out just so you can see it. But yeah, they're super tedious. So pause, give it your best shot, and then we can go over them together. Please try. I promise you it's easier in the long run if you try now. Pause, give it a shot. All right, so it actually only took 4 steps for me to prove that angle 1 is congruent to angle 3, but there was a twist. I had to pull in the idea of vertical angles here. So once I asserted that DI bisects angle NDH because it was given to me, I quickly asserted that angle 2 was congruent to angle 3 by the definition of a bisector, right? That's what a bisecting ray does, or line. It splits the two parts into equivalent bits. So angle 2 is congruent to angle 3. That looks a lot like what I'm trying to prove. This 2 and make it into a 1. And so I started thinking about how are 1 and 2 related. And that's where I noticed if I just look at that part right there, those bad boys are vertical angles. And hopefully you've learned at this point that vertical angles are equal. If you haven't, hey, guess what? Vertical angles are equal. So we know that angle 1 is congruent to angle 2 because of the vertical angle theorem, which says that vertical angles are equivalent. Once I know that, I can substitute that 2 for 1. I can take this out of the equation because 2 is equal to 1 and put the 1 in there. So I have angle 1 is congruent to angle 3 by substitution. Woo! All right, this one, I told you, paragraph proofs. Let's do it. So you just write it out instead of using the table. And so I start by stating what is given. I know that angle AEC and BED are both right angles. So I can right away assert that angle AEC equals angle BED because they're both right angles. I maybe should have put in a line there saying angle AEC equals 90. Angle BED equals 90 because of right angle definition. And so since they're both equal to 90, I can say they're equal to each other. It's a lot of writing. So I went ahead and wrote that they're just equal to each other because they're both right angles by the transitive property. If this is a right angle, that is a right angle, they must be equivalent. So then I can go that AEC equals AEB plus BEC. Here, I'm actually going to number these so that I don't have to keep talking about all the letters. So AEC is made up of angle 1 plus angle 2. And BED equals angle 2 plus angle 3 by angle addition, right? So this is saying that I can split angle AEC up into 2 parts and BED up into 2 parts. Once I've done that, I can say that AEB, 1 and 2, are equal to BEC and DEC, angles 2 and 3, because I already knew that their larger pieces were equal. When I said AEC equals BED, I've basically just broken this into its 2 parts, and I've broken this into its 2 parts. Once I've done that, I can see that there is a BEC on both sides. So if I subtract angle BEC from both sides of the equation, I'm left with AEB equals DEC, which is what I was trying to prove. That's a mic. Just dropped it. These are proofs. They are a pain, but they get easier with practice. So I gave you a quizzes to kind of go over some of the ideas that we talked about here and maybe start looking at some of the justifications. But then honestly, the only way to do this is practice, practice, practice. So there's a PDF that's got a few more of these problems on it, along with an answer key that you should definitely try to get into and practice as much as you can. And I'm serious, guys. This underlies everything that we're going to do for the rest of the year. We prove everything in geometry, so you have to learn how this process works and how this strategy of thinking about things and introducing new information works. So put in the time now. It will pay off huge down the road. And as always, especially this chapter, ask a billion questions. Anything you're confused about, send an email. Whatever you've got to do, pick up a phone, call your teacher, and just put in the time, put in the work. It will pay off. All right.